Very good afternoon. We start our next set of three lectures on module 3, which is properties of a pure substance. In module 1, we looked at concepts and definitions. Module 2, we looked at what are the laws of thermodynamics and how we applied those two problems. We got to a point where we could take a system, show the system boundary, decide which equation to put and what assumptions to make. That gave us a relation between heat, work and properties for either a closed system or an open system. So now if we know any two of those, the third one can be calculated, and that becomes the starting point for analyzing any problem or looking at the performance of any real application. So that's what we will look at. Today we will visit what are the properties of a pure substance, what is a pure substance, and in particular we will look at thermodynamic properties of a pure substance. We begin with by saying that properties of a pure substance could mean a lot of things. We could have physical properties like what you would have come across in solid mechanics or in strength of materials, things like elasticity, modulus, those types. Or there could be electrical properties, resistivity, like that. Chemical properties, that is reactivity. Transport properties, that one comes across in fluid mechanics, main ones there being the viscosity. And then we have thermodynamic properties and also say magnetic properties. So all in all, a material, when you say what are the properties of a material, we look at about 30 to 40 properties of a material, and in any application we decide what properties we want, and accordingly we come across a set of materials that satisfy our requirements. In this course on classical thermodynamics, we are going to be concentrating on the thermodynamic properties. Okay. So first, before we come to the properties, let's ask what is a pure substance and what are its general behavior. So pure substance is something we defined as something where there is the same molecule everywhere in the system. That means at any point, anywhere in the system, whether it's a flow system or a closed system, we say what is the molecule there, we say well it is this particular molecule and it is the same everywhere. So what we exclude by this definition are mixtures of surfaces or substances. So a mixture of say water and sand, or salt and water, or air and butane, we are excluding these. Technically, even air is a mixture, major components being oxygen, nitrogen, and then small quantities of carbon dioxide and other gases. So those would be classified as mixtures, but for the first analysis we will see how certain mixtures can be converted into a pseudo-pure substance whose properties are very easy to know, and that helps us in solving a lot of problems. So we will look at that later on. The pure substance itself can exist in many different phases. Okay, by that we mean that we can get properties which are varying now, and in all cases we can talk of property only when the substance is in equilibrium. So the phase that we are talking of is an equilibrium phase. And there we have three major categories: solid phase, liquid phase, and vapor. So those are the three major phases that we have: solid, liquid, and vapor. On this diagram I have shown something more where an equilibrium state is possible. The word equilibrium is very important here. What it means is that we can have a situation where we have a liquid and vapor in equilibrium. We could have a situation where vapor and solid could exist in equilibrium. So in the first case we get liquid vapor mixtures, So these are now mixtures of a phase. So when we talk of mixture here in classical thermodynamics in this part, when we say mixture, we will mean it's a mixture of two phases. Later on, in the more advanced courses, we'll look at mixtures of pure substances. So we have liquid plus vapor mixture possible, solid plus vapor mixtures are possible, and solid plus liquid mixtures are possible, all individually in equilibrium. And yet one more is possible where all three phases, solid, liquid and vapor, all three exist together in thermodynamic equilibrium. What that means is that when they are in equilibrium, which means that they are in thermodynamic equilibrium, it means that pressure everywhere is the same, temperature everywhere is the same, and species concentration, in our case it is only a one species, that is the same. So that means these mixtures satisfy this property, that everywhere in the mixture, whether you look at a small element in the liquid or a small element in the vapor, or in this case solid and vapor, or in this case in any of the three, in all cases the pressure will be the same, temperature will be the same, and of course it is the same species because we are looking at a pure substance. So if we say same molecule everywhere, essentially we are saying is the same species. So this is something new that is coming up, and it has a very far-reaching implication as far as a lot of applications go. So that's why we need to study this part. So let's look at a few examples where we see this. Okay, before that let's look at what we know as the state postulate. The full details we will not go into it, but suffice to say that for our purpose, for a pure substance, a state is fully defined when two independent properties are known. Any two independent properties are known, which means that the pure substance, the state of that substance is fully defined. And that's what we will look at, that solving any problem, if we need to do some calculations based on the state, we always have to see, well, do I have two properties here? Are the two independent properties there? If not, do I have any more information in the problem by which I can get the property that are not known? So there are two examples. This is the case of a cylinder in a piston arrangement in which there is a piston there, and this is the working substance inside this. So we call this as our system boundary. It includes everything except the walls of the system. Now remember, this definition was very important because if we said that my system is like this, then this boundary, which is the wall of the cylinder, is now part of the system, and when we talk of properties, we would have to talk of the properties of the substance inside here as well as the substance here, and also maybe even any other substance over there. That makes life very complicated, and so we have to be very specific, as I have said all along, that we must define the system very carefully so that it includes the substance that is of interest to us and it is a pure substance. So this we call state 1, and if this comes down here, this is state 2. So in that case, the system boundary now becomes like this. So we know that this is a closed system, and we would apply the laws of the first law and second law of thermodynamics, and we'll say, look, what is the relation between the work, the heat, and the states, the state at 1 and the state 2. That means the properties at state 1 and 2. So if these three, any two are known, the third can be calculated. And that's what the entire exercise of problem solving in thermodynamics becomes. So that's what we need to know, that to get the states, we need the properties. And this information is important because from this thing, we start doing the engineering of this device. For example, if in this process we know that this is the maximum pressure that the substance will take, we know what we can then design, what material should we have here, what material should be there for the cylinder, how thick should it be, how it should be made. All those decisions get taken based on these thermodynamic considerations. Then we have a second example of a flow system, that we have a tube through which a substance is flowing, and this is giving away its heat to the surroundings. Then there is a change in the property of this, and we want to know that what is the relation between the properties at the inlet and the exit state, and how is that related to heat transfer from this. So again, it's the same story that we first decide what are the of these things, what is independent and what is known, what is unknown, and then we calculate the unknown and then do the rest of the design. So like here also we get the same thing. If we know the state that it is going to be here, we say, look, this is the inlet pressure and temperature, this is the outlet pressure and temperature. We have to select a tube which will not rupture at the highest possible pressure or the temperature. And so let's see what materials we can take. What are those materials which are compatible with this substance, and now within that substance, how thick should it be, and all those decisions start to come in. So what I'm trying to say is that the basic thermodynamic calculation is the starting point for the entire mechanical design of the application. So let's see a few pictures of these. Here is a picture of a ship that was launched this week for the Navy. And this ship has, if you read the details of it, it has got 4 gas turbines which propel this ship. We don't see those here, but inside there somewhere, you have 4 gas turbines which are taking in air. It burns the fuel, it generates power. That power drives the propeller of the ship. So like this, there are 4 of those. So that's another example I've given. Instead of the aircraft engine, a ship where the propulsion is done by a gas turbine. This is a photograph of a diesel generator set. What you are seeing here is that this part is the diesel engine. Behind that is the generator which converts mechanical energy into electrical energy. This is the control panel, and in the front, this big square thing, this is the radiator which cools the hot water or hot coolant coming from the engine, cools it and sends it back. So if you want to do the thermodynamic analysis of an engine like this and predict, what is the power it will give, things like that, or what is the heat transfer rate in the radiator, then we assume that the working substance here is something. In this case, we assume that it is air. We treat air as a pure substance and start doing a set of calculations, and we get various numbers on it. Vapor compression system, the chiller of a central AC plant. So what this thing does is, right here in this part, there is a compressor which is operated by a motor. It's further behind this, we can't see that. It compresses the gas, sends it out into this big thing where you have water going through this, which condenses it, and this becomes a liquid refrigerant here. Then it comes down here, it is throttled, and here we have another set of pipes bringing warm water in, which gets cold and goes out as chilled water. This chilled water is piped to different floors in a building, over which then you blow air and we get the air conditioning effect. This is at the heart of all central air conditioning plants. So how do we analyze this system? It is basically the same refrigeration system that we have seen earlier, except it's a much bigger scale and everything is a lot bigger than what we see in a window AC or in a split AC. The last picture here is again something that we saw very recently. India launched a GSLV vehicle, and this is, you can see here, it's on the launch pad, just been ignited, and it's just now taking off. What you see here are on the side these 4 little things, which are strap-on boosters, which have a solid fuel which burns and comes out with a big, that gives a momentum there. And in the center are cryogenic engines. So this thing contains 2 big tanks, one having liquid oxygen, the other has liquid hydrogen. The 2 are pumped and allowed to burn. They produce a high temperature water which comes out and gives thrust, and that pushes the spacecraft ahead. So we won't go into the analysis of this where a solid fuel is being burnt, but the idea of what is the hydrogen and oxygen, how do you get liquid hydrogen, liquid oxygen, why not gas, how does it burn, all those questions require the knowledge of thermodynamics that we are going to be looking at. And we asked, so which are the properties that we want? And here we have a whole series of properties that I have listed. We have come across these. Pressure, temperature, and specific volume is something we came across right in the beginning. Specific volume is same as the reciprocal of density. So either we can say V or rho. So these 3 somehow came very basic things which we got some idea of from school days also. Then we looked at the first law of thermodynamics and came up with these two properties: specific internal energy, specific enthalpy. Then from the second law analysis we came across, now we'll define some more properties. One is specific heat at constant pressure, the other is specific heat at constant volume, and we'll briefly introduce two more properties. One is small g, which is called Gibbs energy, and small a, the Gibbs specific Gibbs energy, and the specific Helmholtz energy. So this will complete all the properties that we require, and the reason for introducing these two is that property relations, that way they evolve, they actually start off from here in one sense, in a mathematical way, and give us equations by which we can calculate all of these. So that's the reason for introducing the Helmholtz energy. So A is called Helmholtz energy, Helmholtz free energy, or Helmholtz function, and you might have come across these in a course in physics or in chemistry. And G is the Gibbs energy or the Gibbs free energy. So these four properties, U, H, G and A, all of which are energy, and specific energy is, we have been using kilojoules per kg. They all represent certain different types of properties of a substance or the properties of a reaction. For example, we know that H was U plus PV, that PV we now know is the flow work. Now, in a laboratory, we cannot measure all of these. This is a big problem. What we can measure is pressure, temperature, and we can independently measure mass and volume, from which we can get specific volume or the density. So those are only real world data that we have, from which we need to get the properties, all of these that we need for this analysis. So what we end up having is a set which is known as the PVT set or the P rho T set, and what we do is we try to fit a mathematical equation to this, and it is not a simple equation like polynomial or thing like that, a fairly complex equation. We try to make sure that it satisfies the property relations and Helmholtz equation, and then we differentiate it and do various operations on that to calculate U, H, S, and then you can even get CP, CV from there. After doing that, 50 years back when computers and calculators were not there, all these properties were tabulated in a table, and a table cannot have continuous data for every pressure, every temperature. There were pressure, temperature data for very discrete, and if one wanted to do a calculation with a property in between, one needed to do interpolation. Gradually that has given way, and now we have all these equations here programmed into a software package. You give a graphics user interface, and you can input two properties and it will tell you all the other properties that you want. So we have reached that point. Some of these packages are available on the web also. Some others are there as open source, some are there with books. So if we use any of these, that's fine. It makes life a little more easier than using tables where you often have to do interpolation. We have software packages, and we also have graphs or charts or diagrams. Throughout we will try to depict every process on a property chart. So that helps us to quickly visualize what is the process and what is it that we are looking at. What is possible, what is not possible. Some very quick answers come out of that. These charts are nothing but taking all the data that we got from these property equations, and we plotted them with two axes, two axes, and the others as running parameters. We will look at those also. Okay, so this is how the whole big plan is, that how from these data, first how do we get this data, what do we understand about the behavior of the substance, and from this data how can we get this data. Okay, so now we come to asking what is the thermodynamic behavior of a pure substance. And broadly we can say that substances behave either as a gas or what I've put in quotes as a non-gas or not a gas. You can call it any of that. Within gases we can say there could be ideal gas or a real gas. In non-gases we of course include solids and liquids, because these are phases also that come in our discussions, and what we call as vapor. We do not call vapor as a gas. Although quite often engineers do speak of a particular substance in a vapor state and they call it a gas. Sometimes it is justified, sometimes the error could be large if you assume it to be a gas. But we will continue with saying that it is a vapor and differentiated that under certain circumstances this vapor can be treated as a gas, which in some situations can be treated as an ideal gas or else as a real gas. If a substance cannot be treated either as an ideal or a real gas, then we have to say that it is in this realm, either we call it the vapor states or the liquid vapor states, or just say that it is a non-gas behavior and we go back to our property. The big difference here is that gases are very nice and easy to work with. An ideal gas is something you learnt in school. PV is equal to RT. The equation of state is very nice, very elegant, very simple. Real gases say, well, this is not the best thing. If you calculate specific volume based on this equation and you actually see what is there in the real world, there could be a difference. That difference could be several percentage points, and that is not good enough. So we start making modifications to this equation. The simplest one being that we introduce the compressibility factor, and then we get even more complex equations where we say that I will add many more terms to this equation to make it more and more realistic about the real gas behavior. So it is still not a vapor, but somewhat of a vapor in some cases, but not an ideal gas. The deviation from ideal gas is large. And so we do real gas analysis. We make this distinction, although I put these two as very different things. There is no hard and fast rule which says that this has to be treated as a gas, this has to be treated as a vapor. Liquids and solids obviously are not vapors or gases, so there is no issue of thinking about those as gases at all. The question then arises is which vapors can be considered to be a gas, and then which gas can be considered to be an ideal. Boundary as to where we make this differentiation, this we will come across maybe in tomorrow's lecture or a little later after that. But for the point being, let's say that there is no hard and fast rule. We say, look, if this number is met, then it is a gas. If it is not, if it is like that, then it is this. So there is a sort of a fuzzy boundary here, and sometimes we have to make our own judgment call in saying, well, okay, I will accept so much uncertainty and I assume it to be a real gas. My analysis is going to be somewhat different than what I have here, but it's good enough to begin with. So this also we will see. What is the way by which we can say if a substance lies in this side or a substance lies in that side. A practical reason why we make this differentiation is that we can broadly classify most of our work to energy devices as gas-based devices or vapor cycle devices. A gas-based device means that the substance all throughout the cycle or the process is always a gas or an ideal gas. In this course, we will assume it to be an ideal gas. We won't worry about real gas. So we will stick with this. And examples are the spark ignition engine, the diesel engine, the gas turbines, aircraft engines, and quite a few other processes that we will say that this is an ideal gas. Now let's look at the analysis, apply the laws, and see how much work it produces, how much heat do I need to give. The analysis becomes very, very elegant and simple because the equation of state, PV equal to RT, is very nice to deal with. So life becomes very much more easier. But it is true only as long as the working substance is an ideal gas, which in our case we assume that it is air, which we assume to be an ideal gas, and so we can do all the analysis here. In more advanced analysis, we start relaxing the fact that air is not a pure substance, it's a mixture, it is not an ideal gas. Let's start modeling it as a real gas, and then you start getting more and more the data that is in better agreement with what you see in practice. But in the beginning course, we do this. We take air as a pure substance, treat it as an ideal gas, and that gives us the handle to understand these devices. The behavior of vapor, and in many cases vapor plus liquid states, has applications like all steam power cycles. So coal-fired power plant, oil-fired power plants, nuclear power plants, all of which would account for like 80-90% of our electricity generation. There we come across a substance, in our case it is water, which is sometimes as a vapor, sometimes as a liquid. And we need to understand how do I get properties when it is vapor and what happens when it is a liquid. All our refrigeration systems, like the one I showed you just now also, that has some processes where we can treat it as a vapor, some processes where it is a mixture of liquid and vapor, and somewhere where it is only a liquid. So that's why this thing comes in. And an example that I gave was the cryogenic engine, liquid oxygen, liquid hydrogen. That is a liquid phase, but then it became a vapor phase and then burnt and it produced some thrust. So all these applications require us to understand the behavior of a substance when it is not an ideal gas. And that is where we will start our discussion today. Before that, let's quickly go through what you probably have learnt about an ideal gas in school days or in a physics course. And then we'll move on to the behavior of substance, vapor cell. So what we have as an ideal gas is that we assume that it consists of molecules which are considered to be a rigid sphere. Each one of them is a rigid sphere. They are moving randomly in space. Quite often they keep hitting each other, and we say that those collisions are elastic. That means it's like two rigid balls hitting each other. Momentum and energy get conserved. As they keep moving around, we say that, look, this is called an ideal gas. Molecule will travel a certain distance. Say this one went here, this came here, and somewhere here they had a collision. And after that, this molecule went there and had a collision with another molecule over there, here. So this is a sort of a distance it was covering between two collisions. And if we know this distance for every collision that happens, and we take the average of that, that is called the mean free path. And the mean free path is much, much bigger than the size of the molecule. Then we can quite happily say that this is a gas-like behavior. Diameter of a nucleus is of the order of 1.75 to 15, depending on the size of the nucleus, into 10 to the power minus 15 meters. The diameter of the molecule itself, including the electron cloud, is of the order of 10 to the power 10 meters, which means that if this is the nucleus, the electron cloud occupies a space whose diameter is 10,000 times the diameter of this. And that's a huge space. And the next molecule, the closest that it will be, is one whose electron cloud touches this one. And when it touches, this could either be a solid or a liquid. This doesn't happen in a gas. These two are very far apart and they're hitting each other. So this gives you an idea about the typical sizes of the nucleus and the size of the atom. 10,000 is a number. The average distance traveled between two collisions in air at 1 bar and say 300 Kelvin is of the order of like 68 nanometers. So remember, this was of the order of 10 nanometers. This is 68 nanometers. So the mean free path is many, many times bigger than the size of the molecule. So that means that what we are saying here as a rigid molecule, there's a little nucleus in this. This is the cloud, this is the nucleus, this is the cloud, and the distance between them is much larger compared to their own diameters, 10 times, 100 times more. And as you go for greater and greater vacuums, this distance keeps increasing. If you look at a satellite orbiting at low altitudes, the distance between two molecules that you will see there is of the order of several kilometers. So that's at the low pressure side. At the high pressure side, as you start pressing these things together, these molecules all start coming closer to one another. The intermolecular distance becomes less, the distance between collisions becomes less, and gradually you start deviating from ideal gas behavior to a real gas behavior, and then finally it is not gas at all. So in liquids and solids, the spacing is of the order of 1 nanometer. In gases, it is 10, 100 times that distance. The difference is that in gases, these are all free molecules. They can roam around randomly where they want. In solids, they are vibrating about their mean position. And in liquids, they are slipping past one another and they take the shape of the material in which they are there, especially in a gravity environment. In a zero gravity environment, that property doesn't exist. Okay, so the ideal gas behavior starts to become a real gas behavior when the distance between two molecules has become such that gravitational attraction between them becomes significant, and it gets the molecules a little more closer than what we would have expected them to be. If they come even more closer, the nuclei begin to repel one another, and so the actual thing will be less dense than what the ideal gas equation will tell us. So these are what we have called the compressibility effects. We'll have a full discussion on this later on. For right now, I just introduced you to this fact that from an ideal gas, as we started compressing it or maybe reducing its temperature, these are all getting closer and closer. And at some point we say, look, I can treat it as a real gas by not using PV equal to RT but using something else. And even after some time after that, we said, look, even using that is not good enough. There's too much error in it. Forget about it. It cannot be treated as an ideal gas. It cannot be treated as a real gas. And we start looking at the concept of vapors and liquids. I'll come back to the questions a little later because we will come to those questions in this module. Certainly. We start looking at we'll do an experiment, a thought experiment, and try to see what happens. And what we will do is this. We will look at a system where we have a cylinder piston arrangement, and in that we have a substance which we will say is water at ambient conditions, 1 bar, say 300, 310 K. And what we will do is figure out, say, okay, now I'll keep on heating it sometime will stop so that there is equilibrium, and then ask the question, the pressure I'm going to keep as 1 bar, what is the temperature? That's the first question. The second question is, what is the state of the substance or the state of water inside this? So what we are doing now is what we call isobaric heating. Okay, the first case we do a little bit of heating, and we know from experience nothing much is going to happen. Water expands a little bit. Thermal expansivity of water is something we have learnt in school. That comes into play, and because of that, this water has expanded a little bit. And say it has reached, say from 300 Kelvin, say about 30 degrees C, it reached say a temperature of 70 degrees C. I'm just putting a temperature. It could be 60, you can take 80, you can take 40, doesn't matter. Think would have happened the same. 30 to 40 to 60, 70, 80. The liquid is still there. So this was liquid. This is also liquid. And its volume increased, but increased very, very slightly. Continue this heating and come to a point we get to this point where this is still there and this is now close to say about 100 degrees Celsius. Again we have, and the pressure everywhere is still 1 bar. 1 bar is there everywhere. Let's see what the states will look like on a plot. So we make a plot where you have two axes there. X-axis we will plot the specific volume or inverse of density, and this side we plot the temperature. And what we will see as these 3 points is that initially say it was here, the volume change was very small, so the graph will not go like this, but will go pretty much steep up like that, and so we'll get a series of states like that. So here's the point that we reached at 1 bar, and all throughout this process we had a liquid. If at any state here, say take this case, instead of heating we cool it, the liquid will contract a little bit because thermal expansion, the opposite is happening, and it will come back to these states and finally come back to this state. Now what happens after we heat it beyond 100 degrees Celsius? What one sees is that the piston suddenly begins to move and move significantly. So it has come up there. And here what has happened now? This amount of liquid that was there, roughly that same liquid is there. And now here, what it meant, there was heat transfer to the system. It converted some of the liquid into vapor phase. Liquid is at 100 degrees Celsius, vapor is at 100 degrees Celsius, this is at 1 bar, this is at 1 bar, but the specific volume of the liquid is this small, the specific volume of this is much larger. So what we will do on this diagram is say, well, I'll just plot the total volume of this. So my mass is the same, volume has increased, so specific volume meter cube per kg, that will increase and increase a lot without any change in temperature. So this state will now start moving along the 100 degrees Celsius line and say come over here. Then we do more heating, and what we'll see is that the piston goes up further, so it comes to another point here. The liquid amount has now decreased a little bit. The rest of it is now vapor. The liquid is at 100 degrees Celsius, vapor is at 100 degrees Celsius, specific volume has increased. Pressure, the temperature is the same, so it will be the state that is now here, we will show it by a point over there. And then we continue heating this. We reach a point where the piston has gone up over there, pressure is still 1 bar, and in this all we have now is a vapor, but the temperature is still 100 degrees Celsius. We can make a plot and say, okay, this thing comes over here, which means that at this point liquid is 0 and vapor is complete, 100%. In all these cases, it was only liquid 100%, vapor 0. In this case, as we kept heating a little bit, or as the piston kept rising, more and more of the liquid went into vapor phase. So liquid amount kept coming down, vapor amount kept increasing, the total mass of the system was still constant. Now we come to the next state. We further heat it, the piston goes up, the vapor occupies all this, but now temperature has become say 110 degrees Celsius. So now from this point to this point, adding of heat started increasing the temperature of the system. Up to this point, heating was increasing the temperature, but in this region, heating of the substance was not changing its temperature but changing its phase. So this point would then show that temperature has increased, volume has also increased, so it will go this way, and we can get a point there. And if you continue heating, these points will keep going like this. Is some example I have taken of water, but one can do the same thing with practically any substance. You can say take nitrogen at 77 Kelvin, or say nitrogen at 1 bar pressure starting from 70 Kelvin, it will do the same thing. Take butane, take a particular pressure and start from say 10 degrees Celsius and start heating it, it will do the same thing. So all substances under certain pressure and temperature conditions will have this behavior. Instead of 1 bar, if I do it at 0.1 bar, what will happen? Or if I do it at 10 bar, what will happen? And 100 bar, what will happen? We will see those things. So now that we got all these states here, what one can do is to join them by a line. So you get one line there, a horizontal line over there, and this line goes like that. And this tells us a lot of things about the behavior of the substance. The most important thing is that from this point to this point, under these conditions, what we saw here was that pressure was 1 bar, temperature was 100 degrees Celsius throughout. Specific volume was changing, pressure and temperature, neither of them were changing. So this point where isobaric heating causes phase change to take place, or isobaric cooling causes phase change to take place, these states are known as saturated states. This is a very important concept. We will keep using it again and again. And it does not have to be at 1 bar or for water. We have examples. We get a lot of substances, including water at different pressures. It will have something like this. These 2 points. This point and this point. At this point, isobaric heating causes increase in temperature. At this point, isobaric cooling causes decrease in temperature. At this point, isobaric cooling, no change in temperature. Isobaric heating, no change in temperature. So what happens is that if you're heating, it increases the temperature. If you're cooling, it doesn't decrease the temperature. Here, if you cool, it decreases the temperature, but if you heat, the temperature does not change. This is quite different from point like this. You heat it, temperature goes up. You cool it, temperature goes down. Same thing here. You heat it, temperature goes up. You cool it, temperature comes down. These 2 points don't behave like that. So this is a point where you have vapor in this, where heating makes it temperature go up, else cooling makes the temperature remain same but causes phase change. This is called a saturated vapor. Or sometimes dry saturated state. And this state is state where the substance is called, this is a saturated liquid. So saturated liquid means isobaric heating will cause phase change. Saturated vapor means isobaric cooling will cause phase change. So we have now two limits that have come up, and then you have all states in between here where the pressure and temperature were both same, specific volume kept increasing. All of these are saturated states, or we may call it wet saturated or just plain saturated state. And here all these states, this substance is said to be a superheated vapor, and these states, this is called either a subcooled liquid or a compressed liquid. So several important things have come out from this small discussion. These are all subcooled liquid or compressed liquid states. This point is the saturated liquid state. This point, the saturated vapor state. In between, all these are wet saturated states. And this point, all these are, okay, now let's take this problem further and say, keep heating it, what will happen? Well, what this picture tells you that it will keep on going up this way. Specific volume will keep increasing, temperature will keep increasing, the vapor becomes more and more superheated until finally we say it is starting to behave like a gas. And if you heat it even more, it will start to behave as an ideal gas. Further on, either of two things can happen. The continuum hypothesis may break down, or the substance may begin to dissociate. O2 can break into O and O atoms. So we will not go to that point. But that's what will happen if this heating were to have continued for a long time. 5 very important concepts: cooled or compressed liquid, superheated vapor, wet saturated state. In a wet saturated state, as you can see from here, this whole state is called wet saturated, but the top part was saturated vapor, and the lower part where the liquid was, that liquid was saturated liquid. So actually this is a mixture of this state plus this state. It is no new state as such. Okay, I will come back to the question. We are just about to come there. In the saturated state, the substance has an interesting behavior, and what we saw was that with heating, pressure and temperature were the same, but specific volume kept increasing or decreasing, whichever way you're heating or cooling it. Which means that if I say that this substance, I have two things, two containers. One is got this much volume, the other has this much volume, and this has this much liquid and this much vapor, and this has this much liquid and this much vapor, and both are at the same pressure and temperature P and T. And so if say I know the pressure and temperature here, tell me what is the specific volume, we now have a problem. Because of the same pressure and temperature, this specific volume is also possible, this specific volume is also possible. So what it is telling us is that P and T are just not enough by themselves to tell us everything about the system, and what we get is that in saturated states, pressure and temperature are not independent of each other. There is a one-to-one correlation between pressure and temperature. but that's only the saturated state. That means if you say, well, what is the temperature? Say, well, 100 degrees Celsius. Then we can look up data that is already there and say, look, the saturation pressure at 100 degrees C is 1 bar. So we are introducing a new concept that in a saturated state, the pressure and temperature are known as the saturation pressure and saturation temperature. And conversely, we can say that at 1 bar, what is the temperature at which phase change will start taking place? Well, for that we say, well, tell me what is the saturation temperature at 100 degrees sorry, at 1 bar, and the answer is 100 degrees Celsius. So by knowing the pressure, we can know the corresponding temperature at which a saturated state can occur, which means that it could be either saturated liquid, saturated vapor completely, or any mass mixture of these two. So this is what is happening. And now we say, well, what happens in the other cases? So for this, one only needs to go to a table, and these properties are well documented, and you say, look, for this material, this is the pressure, this is the saturation temperature. And the pressure in this case is 1 bar. In a minute we will see what happens if it is 10 bar, 0.1 bar, or if the substance is different, everything will fall in place. What we will define now is, well, compared to the saturation properties, what can I say about subcooled and superheated states? So what you are seeing is this, that on this chart, for a state which is over here, the temperature T, or say we will call it, say that T star, this temperature, and compare it with the saturation temperature at the same pressure. Saturation temperature at 1 bar, then this T star we are comparing in this case with 100 degrees Celsius, and we know from looking at it, T star is less than 100 degrees Celsius, and that's the reason why this is called a subcooled state, or subcooled liquid. That means for the given pressure and temperature, the temperature is less than the saturation temperature at that pressure. And very clearly it becomes that all the water we use and drink, its temperature is 25, 30, 35 degrees Celsius. That would be here. The pressure is 1 bar. The pressure saturation temperature at 1 bar is 100 degrees Celsius. And so what we are dealing with every day, what we call water, is actually subcooled liquid water. When water begins to boil, we say, well, what is the temperature there? And at that time we'll say, well, now my water is boiling, my T star is now 100 degrees Celsius. And that's why you keep seeing bubbles coming out, because its temperature is not going up. You can make the gas stove or the electric heater as big as you want. The temperature is not going to go up, only the liquid will keep becoming vapor, and finally everything will disappear. So what we have produced at that point is a saturated state, or a saturated liquid. That saturated liquid became saturated vapor and went and diffused into the atmosphere. That's what happened. Now we look at it in another way. What is the pressure here compared to the saturation pressure at 40 degrees Celsius? Okay, so we have T star and 1 bar, and say T star was 40 degrees Celsius. Then we say, well, what is the saturation pressure at 40 degrees Celsius? And you look up the tables, and this, my guess, is of the order of like about 25 or 20-25 kilopascal. I'm just putting a number there. It's of that order. This is not the exact number. Now we compare this and this. This is less than the actual pressure at which it is. That means you have compressed it, and that gives the name, same state, another name, compressed liquid. So compressed liquid and subcooled liquid mean the same thing. In one case we are comparing the temperature with the saturation temperature at the pressure. In one case we are comparing temperature with saturation pressure at that temperature. So that's a compressed liquid. And we take that analogy a little further, and we come to the superheated vapor state. And what one sees here is that in all these cases, the temperature is more than this temperature. If the temperature T star at any state here is compared with the saturation temperature at that pressure at 1 bar, this temperature is more than the saturation temperature. This tells us that this is a superheated vapor. So it's a very simple thing that if someone says I have vapor at 1 bar and 200 degrees Celsius, tell me what is the state, then you would say, look, 1 bar, the saturation temperature is 100 degrees Celsius, the vapor that you have is 200 degrees Celsius, the superheated state. So it's the superheated vapor. This is the way to find that out. We can define one more parameter here as the delta T, which is T star minus the saturation temperature at that pressure, and this is defined as degree of superheat. And similarly, another delta T of subcooling, this is delta T superheated. If this is T saturation at T star minus T star, this is degree of subcooling. And in any saturated state, the pressure and temperature will be the corresponding saturation properties of each other. We can say one more thing now that we have looked at specific volume. In this picture, we will denote the saturated vapor phase by a subscript F and this by a subscript G, fluid and gas. So specific volume at this point was this, specific volume here was this, specific volume here is this. This is called Vg, this is Vf. Now these are fixed properties that once you say I have 100 degrees Celsius, what is the specific volume of the saturated liquid? It is Vf, that is known in tables. So I ask what is the specific volume of the saturated vapor? In that case, Vg, that is known in the tables. So we can, on that basis, we know that all wet states will have specific volume in between these two parameters. So another way to decide whether it is a subcooled liquid or superheated liquid is that if the specific volume given is V star, if V star is less than Vf, that means it is on this side, this is subcooled liquid. If V star is greater than Vg, superheated vapor, and if Vf and Vg are the limits within which V star lies, then these are all wet saturated states. Or simply we can even just say a wet state or a saturated state. In this region, superheated region, pressure and temperature are independent properties. In subcooled region, again pressure and temperature are independent properties. In this case, they are not. And this is the big change that has happened from what we have learned. And we have to learn how to handle this, because all your power cycles, all refrigeration systems, everywhere we encounter a saturated state. So it's very, very common. Okay, so let's now define one parameter by looking at any saturated state. So we have a system, a closed one. It has got certain amount of a liquid and certain amount of vapor. And this is what is different between different saturated states, is the proportion of these two. And so we have to define something which tells us how much of liquid is there, how much of vapor is there. And for that we will define a new property which is called the dryness fraction. or also known as quality. The symbol is X. It is defined as mass of the vapor divided by the total mass, which is mg upon mf plus mg. Okay, so this is a new definition that we are now putting in, and let's see, can we express it in terms of the specific property? And it's a small little exercise that we can do by saying that the volume of the liquid is capital V G, volume of vapor, vapor is Vg, fluid is Vf, its specific volume is Vg, its specific volume is Vf. And by definition, we know that mg, this is mass, this is volume of the gas divided by specific volume of the gas. mf similarly is Vf upon specific volume of gas. So remember that we are just looking at two things here. This is saturated liquid, saturated vapor. They are in thermodynamic equilibrium. So if we do this thing and exploit the fact that V is equal to Vg plus Vf, and then we substitute this into this, we can get that the total volume is mg Vg plus mf, and we by the definition of X, which is mg upon mf plus mg, we can then put into this, do a little bit of simplification, and what we get is that X is equal to 1 minus X times Vf plus X times Vg. That tells us, this is V. Okay, I will define V here. V is V total upon M total. What it means is that if this is the whole system, then the dryness fraction of this is X, and the specific volume of this is given by this expression. Over here, X is equal to 0. It's a saturated liquid. Over here, X is equal to 1. It's a dry saturated vapor. But taken together in this whole system, we have a dryness fraction which is in between those two numbers. So you have X will always be between 0 and 1. X equal to 0 means saturated liquid. X equal to 1 means dry saturated vapor. So that's the independent property that we were looking at. We can get it from this. And what it tells us is that now for saturated state, T and P are not independent properties, but T and V is okay, because for if it is a saturated state, no matter where it is, there will always be one unique point on this diagram. So if that particular point happens to be here, you know that this is the specific volume, this is the temperature, and you can calculate X from here, and we will see how to calculate all the other properties. Similarly, P and V, these are independent properties. And one can do a similar type of a argument, and we can show that H of the mixture is 1 minus X times HF plus X Hg. The specific enthalpy can be calculated that way. Specific internal energy, you do exactly the same thing. Specific entropy, we do the same thing. So what we have come to a point now where we say that I had independent properties called P, T, V, and now we have added X, U, H, S to that. And what we have said that any two of this is applicable only for saturated state. So if it's a superheated vapor, we don't say X is equal to 1. X is not defined for states other than the saturated state. So if it is in any case for saturated state, that is defined, and these two are interdependent. They are one and the same. Otherwise, in general, any two properties out of this will completely specify the state of the system. So if I know U and H, good enough. State is uniquely specified. We can go back to the property tables and get all the other values: pressure, temperature, specific volume, specific entropy. If P and S are given, same thing. It's an independent, there are two independent properties. The state is completely defined. We can calculate all the other properties. If T and H are given, again, the state is completely defined. We can get all the other properties. The care that has to be taken, as we have seen now, is if it is a saturated state, P and T are not independent properties. They are one property, and either of them with V, or either of them with U, or either of them with S or H, they will completely define the system, or with X. So they are okay. The only thing that is not okay is P and T. V and X is okay, X and H is okay, X and S is also okay. These are all independent properties. But then X is only for saturated state. Let me say that again. Okay, so now we do the same experiment we did earlier, but we do it now instead of at 1 bar, we say we'll do the experiment at 10 bar, and then we'll do it at 100 bar, 200 bar, 300 bar, 500 bar pressures. So that's what we will make the plot now. This side is V, and this side is T. And the first chart that we got was at 1 bar. So I'll just reproduce that over here. This was 1 bar. Now what will happen if we do it at 10 bar? Well, let's say that if I start from the same temperature, 40 degrees Celsius, and increase the pressure to 10 bar, 20 bar or something like that, those states will go this way. Okay, I am exaggerating a lot, but in reality the change of volume of a liquid is very, very small. And you can see the plots, there's practically no difference between these densities. But just to illustrate the point, I have pulled them out. In reality, they are not that far off. Simple reason, in school we have learned liquids are incompressible. That's the manifestation here. Now we heat this liquid, and what we see is that this thing goes up here, and the temperature at which the phase change begins has now increased, and the specific volume at which it is happening has also increased, and it changes phase, and it is somewhere here that it becomes a completely a vapor phase, and then from here it goes off. So this is 10 bar. In between these, we have all the saturated state. So that's what 10 bar did. Vf moved, became bigger. Vg decreased in quantity. The difference of these two, Vg minus Vf, this is often referred to as Vfg. And similarly for specific entropy, specific enthalpy, and specific internal energy. You can call this as specific volume of evaporation, or specific enthalpy of evaporation, what we learned in school as latent heat. So what it tells us is that this thing that was latent heat, which was that much, has now become this much. Specific volume has also gone down. Now what happens if we increase the pressure further? Go to 100 bar. It comes over there. Then you have a series of states that come somewhere there. And then you have the same behavior there. So 10 bar, 100 bar, now let's go to 200 or some 200 bar. At 200 bar, this will come up steeply, come up over there, and this will be here, and from here the states will go off there. So this difference in specific volumes of vapor and liquid phase keeps decreasing as the pressure increases. 10 bar, 100 bar, 200 bar. And then there is a unique pressure for every substance at which this part becomes zero. That means this curve, which is coming like this, has a point of inflection and continues like this. That means at this point, the slope is zero. This is what is called as the critical point. This is a unique property of every substance, and it's all tabulated that the critical point, this temperature is called the T critical. The corresponding pressure at which it happens is P critical. The specific volume at which this happens is V critical. Specific enthalpy at that point is H critical. Entropy is S critical, and like that. So this is unique point. And what it tells us is that if you do this isobaric heating at pressures for water, this is about 220.9 or 220.6 bar, something like that. And at even higher pressures, at 300 bar, this line will go up and just continue like that. It will never come to a zero slope. So this is the all states where pressure is more than critical pressure, and above this point temperature is more than critical temperature, and here we don't call it a compressed liquid or a superheated vapor. We just call it a critical fluid or a dense fluid or a supercritical fluid. Power stations, coal burning power plants that are being built now or have been built in the last 5-10 years in India, they all had steam in the supercritical state. 20 years back, pressures were less than the critical pressure. Those were all subcritical units. And the difference was that in a subcritical power plant, you got to design some part where the phase change takes place. In a supercritical plant, this issue is not there. And by thermodynamics tells you a very simple thing, this has a very big implication on heat transfer and the mechanical design of the boiler itself. There are completely different philosophies for this type of a boiler versus this type of a boiler. The first steam locomotives that operated, their pressures were like 3 bar, 4 bar, somewhere here. And over the last 100, 120 years, these pressures have continuously gone up. Temperatures have gone up, where today's temperatures are of the order of 565 degrees Celsius, which is the supercritical temperature. And this is being pushed to 710 degrees Celsius in power plants that will be built maybe 7-8 years from now. So whole thermodynamics is what is driving this whole thing, because the efficiency goes up, the cycle efficiency. So this is the type of picture we get. And now what we can do in this is that we join all these line points These are all saturated liquid states at different pressures. So we can say that these are all representing dryness fraction 0. Or this is a saturated liquid line. And similarly, we can join all these states on the other side. These are all the states where X is equal to 1. Dry saturated vapor, saturated liquid. In between this are all the wet states. Okay, so what it tells you that as you go from left to right, x goes from 0 to 1. So in this, one can draw lines which are somewhat like this, and say, well, these are constant dryness fraction lines. X is equal to 0.6 is this much, x is equal to 0.7, x is equal to 0.3, they are like that. Okay, all the definitions that we had are valid for all this discussion. This is a saturated liquid. Left of this is a compressed liquid. This side is superheated vapor. In between, we define the dryness fraction. And the top, this is the critical point. So the upper limit of some sort has been set in the properties. As I'm saying, all of this is a huge exaggeration. In the notes, I've given some plots where all of this just becomes very, very small. You can see that in books also, that the effect of pressure on specific volume is very, very small. So that's, as an approximation, one can even say that water at 40 degrees Celsius and 1 bar has the same density as saturated liquid at 40 degrees Celsius. Okay. The next question comes up, what happens below this? If I decrease the pressure to 0.1 bar, 0.01 bar, will I get the same behavior? And the answer is that yes, you will get the same behavior until we reach a point which I will call here, where these lines will end, and this is what is called the triple point. Okay, so the critical point on the top, the lower limit of this is triple point. And for water, the triple point again is like a critical point, is a unique value. Triple point for water is 0.01 degrees Celsius. Triple point pressure is 0.6119 kPa. And you can get the specific volume also. So what the triple point line and all these states, they are all triple states, triple point states, which means that there will be solid plus liquid plus vapor existing on this line. And if you go to temperatures below the triple point temperature, there is no possibility of a liquid. You will only have solid plus vapor formation. Okay, so this is one thing that comes up, that there is a limit at the bottom, the triple point, at the upper, a critical point. If temperatures are between these two values and pressures are between the corresponding triple point and critical point pressures, only those conditions we can expect to see a wet saturated state. It is not necessary that it will always be there, because at this temperature, if we have this pressure, it is a superheated state. But if the pressure is between the, so if the given temperature is between T triple point and critical point and triple point pressure and the given pressure, then we can expect a saturated state to be formed. Saturated liquid plus vapor state. At temperatures below the triple point, we get saturated solid plus vapor phases. The other points where you get solid plus liquid phases. Okay, so that becomes the big picture of the what is called the TV diagram. And it gives us the ability to tell what will be the state of the substance once two independent properties are known. So if we can locate that the state is, say, here, we know it is a wet saturated state, we can figure out where is the temperature, what is the specific volume, and then calculate all the other properties also. If the state happens to be here, we know this is superheated state, what is happening. If the state happens to be here, you know this is a supercritical fluid or a dense fluid, we know what the specific volume, entropy, everything else is there. So this helps us in a very graphical way to very quickly visualize what states to expect for a given pair of properties, provided specific volume is one of them. Okay, so that is one thing that has come out. The real thing looks like this, what I have put in the notes, these would be with you. So what I showed qualitatively, this is the actual numbers on this. And the specific volume I have kept on a logarithmic scale, whereas temperature is a linear scale. And what you see is what I just explained. This is at 1 bar, this is at 5 bar, this is at 50 bar, then you have 220, this is 220 bar, and the top one 300 bar. And so these are all the saturated vapor states, these are all the saturated liquid states. And what you see here is what I was just mentioning, that the way I made the drawing qualitatively, my freehand, is quite unrealistic in what the actual numbers are. You can see here all these points are practically on one another, that the effect of pressure all the way to 300 bar versus 1 bar, there is hardly any difference in the properties at low temperatures here. Only here that you start seeing some difference, but 100 degrees Celsius, the effect of pressure has very little effect on the specific volume. That's why all these have collapsed on one. These are all the saturated liquid points, and you could have, I didn't draw the complete thing, but you can draw this point here, get the saturated vapor line, saturated liquid line, and there is the critical point. The next thing is that this is typical of all substances. You take oxygen, hydrogen, nitrogen, ammonia, sodium, any material, they all behave like this. So what we have learned is basic aspects which are very generic and are applicable to every material. The next drawing that we will extract from what we have learned is what is called the vapor pressure curve. And what we are plotting here, and this plot is with you in your notes. This side is pressure, this side is temperature. And we will translate the same diagram into this form as what are the states that are possible for a pair of pressure and temperature specifications. This diagram ends up getting one line from these lines. What you see here is that at 1 bar the saturation temperature was this much. At 10 bar the saturation temperature was this much. 100 bar it was this much. So in the saturated state between critical point and triple point, we get a relation. So there is, say, the triple point, and we start plotting all these things and we reach the critical point. And this tells us that this is the line that for a given pressure, what is the saturation temperature at that pressure, or for a given temperature and the saturated pressure is sat at that temperature. So this is a unique set of lines which is a one-to-one correspondence between temperature and pressure in saturated states. So we can join these things. Here is the critical point, this is the triple point. At the same pressure, if the temperature is more, or we could have at the same pressure, temperature is less than the saturation temperature, then this is the liquid phase and this will be the vapor phase, which we call the superheated vapor phase. And this line represents x equal to 0, x equal to 1, and any x, any saturated state will lie on this line. Now one goes below this, we start seeing another line, and you start seeing on this side formation of solid. This is temperature, this is pressure, and this will be vapor, this is liquid. Okay, so this line represents states where there is an equilibrium between solid and vapor. So you heat it this way, there is sublimation. In this case, any process that goes from left to right is vaporization. Across this line is condensation. Only one line remains now, the line between liquid and solid state. And here we get two types of lines. One, a line that can either go this way or a line that can go that way. And the slope of these lines are pretty much close to 90 degrees. Very difficult to make out any difference there. So these are two different types of substances. This is a substance that contracts on solidification, and this is the one. So these lines represent the lines where you have equilibrium between a solid and a liquid state. Okay, so this tells us in a nutshell all types of states that are possible, and this vapor means this is superheated vapor. This liquid means it is a subcooled liquid, and just solid in this. And this line is saturated states. All saturated states. That's the vapor pressure curve, and the way it actually looks like, it is there in the notes with you. Okay, this one. So this is the actual plot for water, and you can see the scale here is in degrees Celsius. This side is pressure, logarithmic scale, 0.01 kilopascal to 1 lakh kilopascal. This line, this is the saturated line, liquid vapor line. These points are solid liquid lines, solid vapor line. And this is ice or solid ice on this side, solid phase, and here there is liquid phase. So you can see that actually what I have drawn is again quite an exaggeration just to bring out the point. The fact is that this line is very steep, and for other substances also this line will go slightly back. It's not going to be very much different from this particular line. So it's not like they are curved at very sharp angles like you see here. Okay, so this is the real thing, that what it looks like, a chart. So now we have a complete handle on liquid, vapor, saturated states. We now need to look at how we can construct a bigger picture out of this. For instance, if we take this picture and say, look, now I will, instead of making it on two axes on a piece of paper, I will make T, V, and a third axis normal to the paper, which is P. So you have an XYZ system, and every state point can be located uniquely in that state. And the reason we do it is simple. Because from experiments, we measured P, V, T. And now we try to make a plot. And okay. Pressure here, temperature there, and specific volume over there. And what we are doing is a simple thing. We got lots of data from different researchers across the world over the last 70, 80, 90 years of P, V and T. And that's the only data we have for thermodynamic properties, and we plot it on this curve. So it will be a 3D surface. And this surface looks a little bit complicated. And I'll show the first one here. This is in the notes. This is temperature, this is specific volume, this is pressure. And what we had been drawing was T versus V. We now show it here that every horizontal slice is T versus V at that pressure. So we have stacked up those curves one over the other and joined them by a three-dimensional surface. So you get an inclined surface which is the solid vapor phase, triple line, a critical point which has this shape, and as we go up and keep taking slices, this TV diagram became 0, and beyond that is this surface where it's liquid, dense liquid, and this side is superheated vapor. And this side is solid plus liquid equilibrium, this side is solid, and this is true for a substance that contracts on freezing. Now, water, as we know, is one of the very few exceptions to this rule, and instead of this curve being here, the rest of the curve is the same. This line flips and comes to the back, and that's what you see in this particular picture at the bottom. Okay, this is the triple line, critical point, this is the shape, this surface little here represents solid plus liquid equilibrium, this is solid, that side is liquid, this surface represents liquid, this surface represents vapor. So this is a surface plot. It doesn't look like a very nice surface, it's a little bit complex, but it is not a full 3D thing in the sense that only points on these surfaces are realizable by the TDM. This is what is called the PVT surface. Okay, so if you have this surface, we then fit an equation to this, say P as a function of V and T. And then we do something which we didn't look at in very much detail in the earlier part, which is to use thermodynamic relations. I will give out all these details in module 3, the third part of the notes. We really don't need to go into great detail as far as this part goes. It is not part of this basic course. But what it tells us basically is that all the relations that we wrote down are related to one another in some differential form or the other. And it is that differential form that we exploit using this equation to get all the other values of all the other properties. Okay, so that's what we have there. Okay, there are questions. We will take questions. Well, there's just a few more points that I need to make. In making the properties and putting numbers, we need a reference state. And what has been done over the past many years is that we select a state so that values of U, H, S and all, they are somewhat nice, manageable numbers, and it's not that all of the numbers are 10,000, 15,000, 20,000. So different materials have a different reference state. For water, we say that at the triple point, HF is equal to 0, SF is equal to 0. For most refrigerants, we say that instead of triple point there, we say minus 40 degrees Celsius, HF is set to 0, SF is set to 0. And for cryogenic materials, hydrogen, nitrogen, oxygen, again somewhere near the triple point, we set it to 0, or for a material like helium, we can reference it to even 0 Kelvin. The thing is that as long as we are dealing with differences of enthalpy or differences of entropy, this reference point does not matter. But if you are going to compare something with water with, say, a refrigerant, where the reference points of entropy are different, then you cannot make the same picture. And I'll show that in the next lecture, how that difference comes in. Okay. So we'll stop here and we'll take questions now. Okay, here's the first question. The question is, if H is equal to CP T2 minus T1, is this expression valid for all processes or only for constant pressure processes? Similarly for CV in the case of calculation of internal energy volume. I will come to this tomorrow when we look at the properties of ideal gases. Then I will clarify this. Okay, here is the question. Why, okay, please tell us why it is called compressed liquid. I just mentioned that it's called compressed liquid because the pressure at which the water is more than the saturation pressure at that temperature. So we say it is compressed. The pressure, it has been compressed into a liquid phase. That is the reason. Then there is another question. Why specific volume of liquid is decreasing as we are increasing the pressure? Okay. The question is, why are these points going like this when we increase the pressure? Well, if you look at it the other way, by looking at density, when you take water and compress it, its volume goes down. It becomes denser, so density increases, and specific volume is 1 upon density. So you can see there that when you increase the pressure, the specific volume has increased or decreased, the density has increased. Okay, it says we are plotting T versus V. We are plotting T versus V with the help of experimentation results. Yes. But is it possible to conduct experiments at critical pressure and temperature to get various properties? Okay, so the question is, how did these people get all these properties? So what they did was that they took a vessel, evacuated it, and they put a certain amount of liquid in it. This vessel then had heaters around it, and this whole system was well insulated. And in this there were instruments for pressure and temperature. The volume of this vessel was known, the mass of fluid that we put into it was known, and we could measure pressure and temperature. And that's how these experiments were done. So now if we want to create a critical state, what we now know is that if the volume is known, we know what is the specific volume at the critical state, and these two will tell us what is the mass that I should put in this to generate a critical state. Okay, so it's easier said than done. The critical state, at least mathematically, it looks like a singularity, which it is, and at that point, almost all the equations that are developed also start ill-behaving as differential equations. So now there is a belief that yes, critical point is there, but to exactly get to that pressure and exactly that same temperature and say that it is at the critical state, even within the experimental uncertainties, it's very difficult. But this is the way one would produce a critical state in a substance. Now, having said that, I'll add one more thing, that since this was experimental data, every experimental data has something with it which is called uncertainty. It arises from the basic idea that in this world there is no such thing as exact measurement. So pressure was not exactly measured, temperature was not exactly measured, neither was mass, neither was specific volume, and we quantify how much was what you may call the error. The limits of error is what is the uncertainty, and in all these experiments, uncertainties in say specific enthalpy is less than plus minus like 0.1 to 0.2%. This is extremely difficult to do such good quality experiments, and that is why we believe those numbers, and that is why you and I use it in solving problems, and professional engineers use that in doing all engineering. But inherently, it is never exact. Okay, what is saturated liquid line? Okay, the question is, what is saturated liquid line? On this diagram, and I've shown TV diagram, and tomorrow I will add on to it, and we will make TS diagrams, pH diagrams, any combination of those diagrams. Everywhere we will get a locus of points which correspond to x equal to 0, or which is the saturated liquid. That line which joins all the points of x equal to 0 is called the saturated liquid line. So this line is the saturated liquid line, this is the saturated vapor line. Okay, why does the critical state of a substance occur? Okay, so the question is, why does a substance exhibit a critical state at all? And as I mentioned, this is true of all substances. You take copper, you take zinc, sodium, whatever you have in mind, everywhere you will see these things. But the thing is that this thing happens because you have now increased the pressure to a point where the difference between what is a vapor and what is a liquid has gradually decreased and disappeared. That is what the critical point is actually telling us. So you saw here, below the critical pressure at any point, there was a distinct thing which is called a liquid, where the intermolecular spacing was something. It became a vapor where the intermolecular spacing suddenly increased. This does not happen at the critical point because you have increased the pressure so much that this inhomogeneity that we saw has disappeared. It continuously shows a behavior of one type only, where the intermolecular spacing is now fairly tight and very close, and it doesn't show that it has any ability to become a vapor by getting the molecules very far apart. So that's why this thing happens here. And of course, if pressures are more than the critical point pressure, there is absolutely no hope, because now you have compressed it so much, molecules are so close to one another, they have no chance to get away from each other. How solid, liquid and vapor exist in equilibrium? Okay, so this is a question of how is it that you can have a solid, vapor, liquid equilibrium, or rather, how do we get triple point? Okay, so one word of caution first. When we talk of triple point, or before triple point, when we talk of a solid state, so far I have liberally used the term pressure. Okay, so what it means is that either I have a liquid state which we are cooling and we get a solid, and in liquid we know that if the pressure everywhere will always be constant because it is a fluid. Same is true with a vapor. The pressure everywhere is the same. The moment these substances start becoming a solid, at that point where they have become a solid, the pressure everywhere in the solid is going to be the same. But we know from our knowledge of solid mechanics and stress analysis that pressure is not defined for a solid. So the only thing that we can say then is that if the solid was made at the particular pressure, only at that temperature the pressure inside will be equal to the stress inside, which is the same pressure. If you further cool it, it will not be the same pressure, because stresses will develop, and stresses will cause internal average stresses to be different than what the hydrostatic pressure was. In such a situation, if you have a solid in contact with a liquid, the only thing that makes sense is pressure at the surface or the interface of the solid and the liquid. So this is solid, this is liquid, only here it makes sense. We cannot talk of pressure inside a solid, we only talk of stresses. So this is one caution. The second thing, the question is, how come a solid, liquid and vapor can exist in equilibrium? But think of it like this, that you have a vessel into which we put some solid, say ice, around that there is water, we evacuate this. Now we only have vapor in this. And if we allow it to come to equilibrium and we get that pressure here is triple point pressure, P triple point, the pressure everywhere is that, and the temperature everywhere is the triple point pressure, then all these three will coexist together. And we exploit this in one very important way, not in thermodynamics but in all measurements of temperature, especially in heat transfer. What we can do is, and you can do this small experiment yourself, take a thermos flask, push crushed ice into it, pack it as much as you can, and then pour a little bit of tap water in it. What will happen? The temperature of the water, which was say at 25-30 degrees Celsius, will go down, some of the ice will melt, And if you keep measuring the temperature by putting an instrument in this, you'll see the temperature going down. It will start going to 3 degrees, 2 degrees, 1 degree. At that point, what you do is you drain out that water, and if you have cold water, or sorry, drain out some of the water, or keep that water there and put more ice in it. And then again let it come to an equilibrium. Once you do that, what you have produced is a solid plus liquid equilibrium at 1 bar pressure, whose temperature is 0.01 degrees Celsius, which is the triple point temperature of water. So this is a very easy and a very reliable way to generate a very well-known temperature in a laboratory, and this is an excellent reference temperature. Because any instrument with a thermocouple or an RTD will always require a temperature difference against which you measure a change in a property. Triple point with this is what is called an ice bath. This is a simple and an extremely reliable way of generating 0.01 degrees Celsius. You have in equilibrium solid and liquid. The vapor was at 1 bar, but that doesn't matter too much once you have closed it. Okay? So that's how they exist in equilibrium. And in equilibrium, remember, there are 3 issues that come up here. We have mass of the solid, mass of the vapor, mass of the liquid. And as long as each one of these is in the triple point state, you can have any combination of these masses in this. We cannot just define dryness fraction, but now it's a 3-way thing to be defined. Okay. So that was the answer to that question. Okay, here's the question is, sir, could you explain importance of critical point in engineering field of application? Okay. Okay, quickly I will do this and I will pick it up tomorrow again. What is the importance of critical point temperature? As I mentioned, we are designing, say this is a, I'm going to jump the gun, tomorrow I'm going to show this. So this is the temperature and entropy diagram. The saturation dome looks like this. If we design something to generate superheated steam, we have to design something that will heat the liquid part. Then we design something that will do the evaporation, where there is a big phase change taking place. Phase change means a big volume change. And then superheating part. So the design of the boiler becomes 3-part design. But if you have a supercritical boiler, this will go off like that. Which means I don't need to design 3 different things, only one thing. And the reason why we design it is that when you use steam at this condition versus a steam at this condition, the thermodynamic efficiency of this or cycle built around this is going to be much more than the thermodynamic efficiency of this cycle. So that is the reason why traditionally pressures have gone up, temperatures have gone up, and we are coming to supercritical pressures and temperatures. The limiting factor though, thermodynamics tells you can go as high as you want in temperature, but we do not have materials for making a boiler that can withstand such high temperatures at high pressures for 20-30 years. That's the challenge. Okay. So with that we will conclude this session. Tomorrow we'll look at some more of the property diagrams, take some more examples, and then we will go on to see what is ideal gas behavior.